All right, these are going to be the solutions to the relative motion practice. And the one thing to remember as we're, one thing to remember, not the one thing to remember as we're doing this, if we're doing something, so relative to the blue car, the blue car has zero velocity. So relative to yourself, you think you're not moving, and everything else is moving around you. So this idea is going to drive what we do as far as figuring this out mathematically. Now, for A, what we've got is a race. We have a red car going at 120 meters per second, racing a blue car that's going 100 meters per second. And we know in watching this that the red car is going to pull ahead. So what we want to know first is, relative to the blue car, how fast is the red car going? Now, the blue car doesn't see it as going 120 miles an hour because the blue car thinks he's at rest. So the blue car sees the red car pulling ahead. This is what he sees, 20 meters per second faster. So really, the velocity of the red car to the blue car is 20 meters per second in the positive direction. And then relative to the red car, the blue car falls behind (20 meters per second. It looks like the blue car is going away at 20 meters per second. That's in that backwards direction. So the velocity of the blue car is negative 20 meters per second. Now notice that that's the same relative velocity, 20 meters per second. It just has a different direction. And one other thing I want you to notice is that because they're going in the same direction, they're both going forward, the relative velocity is the difference in their velocities. Now, assuming the cars start at the same spot, how far ahead of the blue car will the red car be after 20 seconds? The best way to do this is to say, okay, I just want the distance between them. So their displacement is going to be their relative velocity, 20 meters per second, times the time, 8 seconds. It's going to be 160 meters ahead. We're just going to multiply those two things together to get it. Part B, towards the end of the race, the red car moves with 120 meters per second. So we have the red car going at 120 meters per second. And then the blue car is moving at 140 meters per second in the opposite direction. Red car, 120 meters per second. Blue car, 140 meters per second in the opposite direction. So we want to do this again and look at the velocity relative to the blue car. Now, this is a little tricky. They're heading towards each other. When they head towards each other, it's like their velocities add up. So the blue car thinks he's at rest and sees the red car really moving towards him very, very quickly. It's actually going to be those two things added together. So if you're in the blue car, you see the red car heading towards you at 260 meters per second in this direction. Now, there is a mathematical way to do it. So what we said was that from the blue car's perspective, he's not moving. He has a speed of 0 meters per second. So what do we have to do? Oh, and then this 140, because it's in the backwards direction, we got to make that negative. So in order to cancel out that 140, we have to add 140 meters per second to make it seem like the blue car is at rest. That's how we would adjust the velocity to get into the blue car's reference frame or point of view. But if I want to be in that same point of view, I have to do the same thing to the red car. So I'm going to add 140 meters per second to the red car's speed, and I see that the red car is going 260 meters per second, and it's positive. That's how we would find that relative velocity of the red car. We'll draw some conclusions in a minute. So if we're going to do the same thing relative to the red car, mathematically speaking, what we want to do is get the red car to have a velocity of 0. So I would subtract 120 meters per second from the red car to get into looking at how the red car sees things. But if I want to look at how the red car sees things, I have to subtract that 120 meters per second from everything. So negative 260 meters per second. And that's how I would get the blue car's velocity relative to the red car, negative 260 meters per second. Now, what we notice here is that because these two are heading in opposite directions, their relative velocity is the sum of their velocities. We're going to add them together. When they're traveling in the same direction, we subtract them. When they're traveling in opposite directions, we add them. Assuming the cars start 780 meters apart, how long will it take before the cars pass each other? The best way to do this is from one of the car's perspectives. So let's go from the red car. Let's go from the blue car. The blue car, put here, remember the blue car sees his velocity at 0. The red car, from the blue car's perspective, has a velocity of 260 meters per second. And the red car is 780 meters away from the blue car. So from the blue car's perspective, what he's looking at is, all right, the distance separating us is 780 meters. The velocity of the red car is 260 meters per second. And I want the time it's going to take for the red car to get here. That's the information we're going to use. It's from the blue car's perspective. You could do the same thing for the red car. And we know that the time, you know what, this is a good opportunity to show that again. If I have velocity equals change in displacement over time, and I want time by itself, multiply both sides by time. Now I have time times velocity is equal to delta x, which we use quite a bit too, but if I want time by itself, we divide both sides by the velocity, and the time is equal to delta x over the velocity. So we have 780 meters divided by 260 meters per second, and that ends up giving me 3 seconds for him to cover that. So everything that we wrote in black is stuff that we've done before with velocity and displacement. The trick to this one is looking at it from the perspective of the blue car so that we can get some numbers there. Part C, the two cars start at rest and then drive away in opposite directions. The red car moves at 100 meters per second. The blue car goes at some velocity that we don't know, and after a bit they end up 600 meters apart. What's the velocity of the blue car relative to the ground? Now, what we can do is look at what we really know about the red car. The red car has a velocity of 100 meters per second, and it's moving for a time of 4 seconds. So its displacement is going to be, according to this, velocity times time. So the red car is going to go 400 meters. But they're 600 meters apart. So if they're 600 meters apart, that means the blue car had to travel a distance of 200 meters in a time of 4 seconds. So the velocity of the blue car is 200 meters divided by 4 seconds, or 50 meters per second. So we have an airplane that's flying with a velocity of 80 meters per second relative to the air. So the airplane is flying to the north at 80 meters per second with the air. And I know that the wind is blowing to the south with a velocity of, it's too big, with a velocity of 12 meters per second. So the airplane thinks it's going 80 meters per second in the air. The air is going back at 12 meters per second. This is like the moving sidewalk problem. So if he's going 80 and the moving sidewalk's going 12, what he's really doing is the difference between those two things. What he's really doing is moving with a speed of 68 meters per second relative to the ground. Okay? So in this case, when they're moving in one another, we're going to have to subtract that. The relative velocity is 80. They're moving in opposite directions. That's those two things. That's the difference between those two things. After an hour, the wind shifts from that and blows to the north with a velocity of 8 meters per second. So we have our plane. Our plane is still going 80 meters per second relative to the air, and the air is going at 8 meters per second in the direction of the plane. So now the plane is going 88 meters per second. So the difference between this and what we were doing before is that we are given the relative velocity, not the actual velocity. So when we're given the relative velocity, we're going to add the relative velocity to the velocity of the other thing to find out what the plane is doing. As the airplane reaches the airport, the wind is blowing from east to west with a velocity of 60. What's the resulting velocity of the airplane with respect to the ground? So the airplane is going 80 north. The wind is blowing it 60 towards the west. This is going to be the resultant velocity of the airplane. I'm going to put a star by this because we haven't really done right triangle stuff yet. So consider this bonus level material a little beyond where we are. It's just an added piece. When we have things at right angles to each other, we have to add them with Pythagorean theorem. So this would be the total velocity. That total velocity would be the square root of 60 squared plus 80 squared, or 100 meters per second. And again, if you don't like that, don't worry. Just before landing, the wind's blowing the velocity of 18 meters per second. What's the resulting velocity of the airplane relative to the ground? So we've got 80 this way and 18 this way, and we want that velocity. Again, that total velocity is going to be the square root of 80 plus 18, 80 squared plus 18 squared. And when you calculate that, it comes out to be 82 meters per second. But again, this is bonus level stuff, and if you don't like it, just skip it and don't even worry about it. All right, last one. A train travels to the north at a constant velocity of 40. Stowaway boy walks along with the train. If the boy walks towards the front of the train at 6, what's his velocity relative to the ground? All right, so the boy's walking at 6 meters per second with the train that's going 40. If you're on the ground, you see that as 46 meters per second. They're in the same direction, so the velocities are going to add together to get that total velocity. If he walks towards the rear of the train at 8 meters per second, so we have the train going 40 meters per second, and the boy on top going 8 meters per second. Again, that's relative to the train. So his resultant velocity is going to be 32 meters per second. It looks like he's going a little slower than the train. If he were on top of the train running backwards at 40 meters per second, he would look like he was at rest. Now, as the boy walks towards the front of the train at 5 meters per second, second train moves towards the first train at a speed of 20. What's the velocity of the boy relative to the second train? Now we have lots of stuff happening. So here's our first train with the boy on it. So let's just deal with him right now. The train's going 40. The boy's on top going 5 relative to the train. So the boy's real velocity is 45 meters per second. And then we have a second train traveling towards the first train with the speed of 20 meters per second. So relative to the second train, so from this train's perspective, the boy is coming at him at 65 meters per second. So we had to do two things. We had to do the how fast is the boy going on the moving object. That's where we either add or subtract their velocities. And then we had to do, and then how fast is that relative to the other train. All right, that's what we've got.